Okay, so we are computing Hilbert series, right? But we're computing them in this very special case of remember I call this the Stanley-Reisner ring. So it's the quotient of the polynomial ring by a square-free monomial ideal, which we know corresponds to a simplicial complex delta, right? And last time I proved this formula for you, saying that the finely graded Hilbert series is given very explicitly. Okay. So in this example over here, I think this is the one that I did last time. So this is the simplicial complex, right? Here are A, B, C, D, and E are the vertices, and then we have faces. What we see here is that this is supposed to be a hollow tetrahedron, right? So all the faces of this tetrahedron are part of the simplicial complex, but the tetrahedron itself is not in the simplicial complex. And we said that if we want the finely graded Hilbert series, well, that's going to come in 5 variables, one for each one of the vertices. And we choose to call the variables the same as the vertices because it just makes life a little bit easier. And so what we do is that for each face, we write something. So for the empty face, we write 1. For each vertex, we write vertex over 1 minus vertex. For each edge, we write the product. For the edge AB, we get A over 1 minus A, B over 1 minus B. And so we do this over all vertices, all edges. And then we do that for all the triangles, but there are several triangles. But then there's no tetrahedra, so we stop there. Okay, and we write this big whole thing out, and that's going to be the Hilbert series. Okay. By the way, I wanted to show you that if you take this expression, it's a big expression, right? There's 1 term here, 5 terms here, then there's 9 terms here, and 4 terms here. So this is a big thing. But when we really write this out and multiply it out and everything, you get the following answer. By the way, this is all in the notes, so you don't need to write it down if you don't want to. It's kind of long, but the point is that it's not that long. I mean, a priori, maybe we expect it to be longer because, like I said, there's over 20 terms here. Did I say that? There's about 20 terms. I don't know. I didn't count exactly. And then when we clear denominators, we might be making a big mess. Okay. But it turns out that in the end, we just have these 1, 2, 3, 4, 5, 6, 7, 8 terms. Okay? And there is a nice explanation for this, and we will see how to understand all of these terms. I mean, this is a big formula, but we're going to see how to get this shorter formula. Okay? But this is what we proved last time. And then I was in the middle of telling you how this goes for the coarse Hilbert series. Which might be the one that you care about. Very often we only care about the one in one variable, the one that keeps track of degree. And I said that this was just given by the H-polynomial of the simplicial complex divided by 1 minus x to the d, where d is the dimension. Yeah? Is it not? So the question is whether this was the example from last time, and honestly, I don't know. Does anybody have notes from last time? Well, anyway, so this is the example from this time then. So let's go over what the example is again. So it's a hollow tetrahedron, so that means that we have 4 triangles, one for each face of the tetrahedron, and then a bunch of edges and a bunch of vertices, which are the ones that you see there. Okay. Actually, the next thing that I want to do is talk about H vectors, and so maybe what we should do is compute the F vector here and see that we get that formula over there. Okay? Because how am I going to prove this formula? Well, the thing is, I mean, like I said, sometimes you don't care about this whole thing. Sometimes you care only about the smaller expression in one variable. But the point is that if you're able to write this one, then the other one follows automatically. Because remember that to go from the fine series to the coarse series, all you have to do is set all the variables equal to x. Okay? So that means that if I want the coarse series of this guy, then all I have to do is set x for all of the variables, and that'll be my answer. So let's see what we get. We get a 1. Then we don't have anything of degree x. Then we have one thing of degree 2, so that's going to give me an x squared. Then we have 2 guys in degree 3. Please double check what I'm doing here. It's a little hard to see it on the board. And then I have, of degree 4, I have minus x to the 4th, and then 3x to the 4th, so I get 2x to the 4th. And this is my Hilbert series. Does that look good? Did I make any mistakes? I'm sorry? To the 5th, that's a mistake. Okay. So maybe that's a first interesting thing, that I got 1 minus x to the 5th in the denominator, but I was anticipating to get 1 minus x to the d, right? Where d is the size of the. I guess I didn't say what I meant by d here. So d, this integral complex has dimension d minus 1. So d is the size of the largest set. Size of the largest set in delta. But now remember that, for example, a set of size 3, ABC, represents a triangle which is 2-dimensional. Okay? And so this is what we call the dimension of the simplicial complex plus 1. Okay? So here, this is a 2-dimensional simplicial complex, right? Because the largest faces are triangles. So that means that I should have expected a denominator of 1 minus x cubed. And I should tell you that I'm slightly nervous because I didn't try this ahead of time. But I'm not too nervous because, for example, I know there's going to be some cancellation. Because if you look at the numerator, you can see, for example, that it's a multiple of 1 minus x. If you plug in x equals 1, you get 0. So this should cancel and give us the right answer. What I'm nervous about is that I'm going to do some computations that I haven't done ahead of time, but we're going to do it. So we are going to compute the f vector and the h vector for this guy, and that way we will remember how this goes. Okay? So what's the f vector? Remember, I defined that to be just counting the number of faces of each dimension. Okay, so the f vector has, when dimension minus 1, you have the empty face. You always start with that. So 1 empty face, then you have to say how many vertices you have, and so there's 5 vertices. Then you have to say how many edges you have, and here I really need your help so I won't make mistakes. I guess the tetrahedron has 6 edges, and then I have 3 more. So that's 9 edges. And then I need to count how many triangles I have, which are the 4 faces of the tetrahedron. Right? And then I need to count how many tetrahedra I have, but actually there are no tetrahedra, so I stop there. Okay, so this is the f vector. And so just to remind you how that goes, in general, I said that the f vector is f minus 1, f0, up to ft minus 1, where fi is the number of I-dimensional faces. I call this the f vector. Okay. The next thing I did is I made a polynomial out of this, which I'm just going to call f delta of x, and that's just going to be taking this guy and making a polynomial of degree d out of it. Okay, so here the indexing is a little bit weird because we want this to be a polynomial, and so we don't want to put an x to the minus 1 here. And so that's why I say f minus 1 x to the 0 plus f0 x to the 1, etc. So this guy is called the f polynomial. Okay, so I do that here, and I get that the f polynomial in my variable x is given by 1 plus 5x plus 9x squared plus 4x cubed. Okay, that's the f polynomial. Then the next thing I do is that I define this h polynomial. And I define that to be something which is equal to so it's kind of a variation of the f polynomial. Okay. So it looks almost like the h polynomial, but I tack this on. Okay. And so I would have to go and do that over there. Okay. Now I should tell you that it's a very easy computation to see that this is the same thing as 1 minus x to the d times the f polynomial evaluated at x over 1 minus x. Okay. So this is called the h polynomial. And so you can do it in whichever way you want. You can do it like this, or you can plug in x over 1 minus x and sort that out. And well, you see that this is easy to do, but it takes some work. Okay. And I want to give you 2 tricks for computing h polynomials. And part of your next homework is going to be to show that these tricks work. So there's a trick that I learned from Richard Stanley and a trick that I learned from Marx Kandera. I know that Stanley's trick is Stanley's trick, but I don't know if Marx made this up or not. But they go like this. So 2 tricks to compute the h polynomial. By the way, actually, can someone do me a favor and divide that numerator by 1 minus x squared and tell me what you get? It should be, the denominator really should be 1 minus x cubed, right? So that means that the numerator has to be a multiple of 1 minus x squared.
1 plus 2x plus 2x squared.
How did you guys do it so fast? So this is good, right? And this is a good reason to have computers right in front of you. You can do this. So what is it? 1
plus 2x plus 2x squared.
Plus 2x plus 2x squared over 1 minus x cubed. And so that means that this guy must be the h polynomial of our simplicial complex. Okay? So that'll be a sanity check. So 2 ways of computing h polynomials. So first I'll show you the one that I learned from Marx Kandera. Like I said, pay close attention to what I'm going to do because you have to prove that this works. So what you do is that you take the f polynomial. Then the first thing you're going to do is you're going to just reverse the coefficients. Okay, reverse coefficients. So that means I'm just going to make this guy be the x cubed, this guy be x squared, this guy x, and this guy like this. Okay, that's the first step. The second step is that you're going to take x and plug in x minus 1. Okay? So what you get is x minus 1 cubed plus 5 times x minus 1 squared plus 4. So we can either compute this or type it up into whatever program we have in front of us. We get x cubed plus 2 What is it?
1 plus 2x plus 2x.
Like that?
Oh.
Did I do something wrong?
Oh, of course it should be 1 plus 2x is 2x squared. So
I did something wrong, right? Okay, well, I guess you guys are going to have to see what I did wrong and why this works. But you do this. Do you? 1 plus 5 Oh, okay. So I'll tell you what the last step is you reverse the coefficients again. And so when you do that, you get 1 plus 2x squared plus 2x plus x cubed. And so somehow we don't really want this, which means something went wrong along the way. Anyway. So we'll see. We'll see what went wrong. Is the f vector right? Well, we'll see. So I'll show you the other method. It's also kind of cute. So what you do is this. You Oh, I see what I did wrong. Well, anyway, you can please double check this and see where the mistake is. We should be getting this answer, I think. So what do you do? Stanley's trick says the following. Write your f vector like this. Okay, this is the f vector, and you're going to do kind of a Pascal's triangle. But the rule is not the same. The rule is that you're going to take this guy minus this guy and put it here. Okay. So 5 minus 1 is 4. 9 minus 4 is 5. 4 minus 1 is 3. 4 minus 5 is minus 1. 5 minus 3 is 2. 3 minus 1 is 2. And whatever the mistake is that we did somewhere over here, the point is that this thing that you get here should be your H vector. Okay? So you're supposed to get the same answer here, and here, and here. Okay. So let's get it right in the forum, but I guess that's what I get for not doing this ahead of time. But hopefully you see the point. The point is the point of the theorem is that if you want to compute these Hilbert series, it's very easy and combinatorial. All you do is you count the faces of the simplicial complex, and then H delta, I don't know anymore what H delta is supposed to be. I think it should be this guy. But the point is you do this combinatorial thing, you get the correct H polynomial, and that there's your formula. Okay? And that's a beautiful formula because it basically says that this algebraic quantity that we wanted to understand, right? This is our algebraic measure of our algebraic ideal, but this says that we can just measure it combinatorially. You just count faces and find the H polynomial, and that's it. Okay? So that's what the statement says. And just to define the last thing, the H vector is the coefficients that appear here. So the H vector looks like this. So that's the idea. Now let's prove this theorem then. And since we proved the first part already, the second part will actually follow pretty easily. So given that the first part, that the fine Hilbert series is that, then the proof for the coarse series goes like this. It says what I have to do is plug in the same variable x for all the variables xi's that appear in my first formula, right? So I need to take sum over sigma and delta, product over I and sigma, and then x over 1 minus x. Okay? I just plug in every xi equal to x. I'm going to smoothly switch batteries now. So we do that, right? Now, the point is that this is actually a lot easier because this product over here, we have the product over all I sigma of x to the 1 minus x, so that's just x over 1 minus x to the size of sigma, right? So let's do that. So this is sum of x over 1 minus x times the number of elements of sigma. Right? But then we're going to say the following. We're going to say, okay, how many times does x over 1 minus x to the I appear? Well, it's going to appear once for every face that has I elements. And how many are there? Well, if you have I elements, that means that you're of dimension I minus 1. And so that means that this term appears exactly f I minus 1 times. And then I just say that if I want to put a common denominator then that common denominator is going to have to be 1 minus x to the d. And so I have to do this. And this is exactly my H polynomial by definition. Okay. So that's the proof of the coarse Hilbert series. Okay. And so you see the point is that we already did all the hard work with the fine Hilbert series, and then this one is just a very simple consequence of it. Okay. By the way, you might wonder, for example, I mean, a natural question is what is this H vector? What am I doing here? I think you'll agree that the F vector is a very natural quantity, right? If you want to measure your simplicial complex, it's natural to say, well, how many faces do I have of each size? But what is this H vector? And what is this H polynomial? It's some mysterious thing, and it looks like I just defined it so that this theorem works. And, well, that's not too far from the truth. But we'll see several things about this H vector that make it very nice. And one thing that I would like to mention, and one reason why this H vector is very nice is the following. It's a theorem of Dehn-Sommerville. I think it's double M. And it says, if a simplicial complex delta is the boundary of a d-dimensional polytope, then this H vector has the property of being symmetric. And so I hope that convinces you that there is something about this H vector. The other nice thing about this is that actually they prove that these are the only possible relations between the F vector of a polytope. So let me say what I mean by that. We're talking about the boundary of a polytope, right? And we're saying, okay, well, how many faces do I have in each dimension? And I call that the F vector. What this is telling me is that it's giving me d over 2 equations between the F vector. If you think about it, each one of these H numbers is some combination of the F numbers. Okay? And so that means that each one of these very nicely encodes an equality involving the F vector of a polytope. And that means that if you want to know the F numbers of the whole polytope, actually you only need d over 2 of them, and the other two are determined by this. Okay? And so this is really, and another theorem of Dehn-Sommerville is that this is it. So these are all the possible relations between those F numbers. You really need half of the F numbers, but you don't need the other half. Okay? And so I think this is good evidence that these quantities are natural. And the proof of this is topological, which means that these guys have some kind of topological meaning. So that's just to give you an idea of what we're talking about here. These are called the Dehn-Sommerville relations. Okay, so we're going to switch gears a little bit now. I think I won't need this anymore. Might not even be right. The point is this. The point is that if you remember, one time in class, seemingly in the middle of nowhere, I defined homology for you. And this was an algebra class, and all of a sudden I defined a word that really seems to belong in a topology class. But I really want to keep making this point to you that you don't get to choose where your mathematics comes up. And we're in an algebra class, but topology comes up, and so we have to deal with it. So it's time to learn some topology. The point is that we're doing these computations of free resolutions, right? But what turns out, and is the truth behind all of this, is that we're kind of in disguise computing homology groups. And so what I want to do for the next couple of classes is teach you a little bit about homology groups, show you how to compute them, and then after developing a little bit of algebraic topology, then we will be able to say some very nice things about this. So here's kind of a crash course in algebraic topology. Of course, I'm going to only scratch the very, very surface of this. But what's the idea? You probably heard the silly joke of how a topologist is someone that can't tell their donut and their coffee mug apart. That's kind of what we're after here. What topologists do is that they study surfaces or topological spaces, and they want to know whether they're the same or not in the topological sense. And that's kind of the sense that, for example, we think that, so in terms of topology, here's a coffee cup, and here's a donut. And the reason that a topologist would tell you that these are the same things is that if you can imagine these things being made of, how do you say plastilina in English? Play-Doh. Yeah? Play-Doh, right? So, yeah, very. Is there a non-commercial word for Play-Doh? Clay, but clay is something else, isn't it? Modeling clay. Let's talk about modeling clay. Okay. So if you take a coffee cup made of modeling clay, then you can imagine deforming it and making it into a donut in a nice and smooth way. Okay. And so the technical word for this is homeomorphic. And we won't care too much about what that means. That would really take us into a deeper excursion into topology. I just want you to think that basically things are kind of the same if you can kind of deform them to look like each other. So, for example, a square is equal to a circle, topologically. Or a coffee cup is equal to a donut. But, for example, a circle is not equal to a disk. Okay, this guy's, so when I draw it like this, it's empty. So there's a hole in the middle. And this doesn't have a hole in the middle, so you can't, these guys are not really the same thing. You can't deform one into the other. Okay? So when I do this, this means that this is empty. Hole, hole, hole. And here's a hole, and here's a hole. Right? Or, for example, here's something, here's a circle with a hole in it. And, I mean, I guess the natural question is, are we just counting holes here? But it's not exactly true, because if you think about this, if we think about a circle with a hole in it and a sphere that's empty inside, well, we can call these two things holes, but I don't think you can say that they're the same thing, right? These are not homeomorphic. You can't take a one-dimensional circle and make it into a two-dimensional sphere. By the way, when I say the sphere is two-dimensional, I say that because the surface is two-dimensional, right? If it was the ball, then it would be three-dimensional. Right? So these things are not equal to each other. And there are more subtle things, for example, but I think you'll agree also that a sphere is not the same as a donut, right? By the way, one thing, what I mean here is not a donut. What I mean here is what's called a torus, which is a donut that's empty inside. Okay. So these things are both empty inside, but they are different because this guy really has a, you can put your finger through it, and you can't put your finger through that. Okay. So what is algebraic topology? Well, the thing is that we want to make science and not just point and say these kinds of things. And so an algebraic topology, what you do is that you start with some topological space X, and you want to associate to it some algebraic object. Let's call it A of X, in such a way that if X and Y are equal to each other in this topological sense, then the algebraic objects will be the same in the algebraic sense. So here we're not going to have equality, but we'll have some kind of isomorphism. And it depends where we're working, right? So I'm saying algebraic object very vaguely because this might be a vector space, this might be a group, this might be a ring. And depending on what you're doing, you really do things in a different way. Okay? So here I might mean as rings, as groups, as vector spaces. Who knows what I mean? I mean, I could mean any of these things. And here I could also mean different things, and this is where we would go into topology, but I might mean homeomorphic. I might mean homotopically equivalent. I might mean different things. But what's the point? The point is that we actually do know, we have good techniques for showing that algebraic objects are equal or different from each other. Okay? So for example, if I can associate an algebraic object to a sphere and to the torus, a group, for example, a homology group, for example, then if I show that the homology group of this guy is different from the homology group of this guy, then I'm going to know that they're topologically different, because if they were equal, they would have the same homology group. Okay? So that's in a nutshell what algebraic topology is about. Okay? Any questions about that? It's a very general discussion, but that's kind of what we're after here. So okay. Now, one thing that is very handy when you do these things, and we want to associate, for example, an algebraic object to a topological space. Okay, but our algebraic objects tend to be kind of discrete in nature. I mean, we kind of think of them in concrete ways a lot of the time, and definitely in what I'm about to do, which is homology groups, we want something very discrete, and so we want a discrete description of this. What do I mean by discrete? I mean something that belongs in this class more than in a calculus class. It's a very vague description. But then, if you think about it, it's kind of the same thing as if you really had an application and a computer scientist really had the surface of a face. Well, how would you deal with that? How would you store the surface of a face in a computer? You guys might be aware that what they always do is triangulate. Right? So storing the whole face is impossible. So what they do is that they just put a little tiny triangular grid, and they keep track of all the little triangles, and then that's what they store, and then we always get these kind of triangular approximations of surfaces. Okay? And that's the same thing that we're going to do here. We're going to analyze surfaces, and the way we're going to do it is we're going to triangulate them, and that way we'll be able to, that way they'll look like simplicial complexes, right? Which is what we know how to deal with. So for example, how do I triangulate a full square? Well, for example, that's not a simplicial complex, but I can make it into a simplicial complex by just adding this. And I haven't really changed the space. I mean, the underlying space is the same. I just subdivided it a little bit. Topologically, I haven't done anything. And now I can think of this as a simplicial complex. I can label it A, B, C, D, and I can say the faces are AC, sorry, everything but AC, right? AD, AB, BD, ABD, etc. So we like to, the usual trick is to triangulate the first trick, to triangulate X to make it a simplicial complex. Okay. And this might be a little bit tricky. For example, one thing that I would like you to do is, I mean, for example, how do you triangulate a sphere? So a sphere is a two-dimensional sphere, but the inside is empty. Okay. So how would you triangulate that guy? Let's say, what's the smallest triangulation of that guy? How many triangles do I need? 4? How do you do it with 4? You basically just pick 4 points and make a tetrahedron out of them, right? And this is going to be hard to draw, but maybe this point is in the back. And so I do this, I do this, I do this, and then I do that. This picture is not very good, is it? Because actually, what I need to do is go around here. And now you see that the surface of the circle has been split into 4 things that are curvy triangles. They're not really triangles, but for combinatorial purposes, they are triangles. Okay? And you can think about it for a second, and you'll see that with 3, you can't do it. This is really the smallest thing you can do. Okay? And I would like you very much to think about how you would do this for the torus. So I want you to triangulate the torus and really do it, and you're going to have to make a nice picture and see what's the cheapest way that you can do it in. The one that uses the smallest number of tetrahedra. Not tetrahedra, because the torus is a two-dimensional thing. So how many triangles do you need? Triangulate the torus with as few triangles as possible. But then the point is that what we want to do is now take this simplicial complex, which is a combinatorial thing, and just using combinatorial techniques, we want to detect topological characteristics of this guy. Okay. So then the first trick is to triangulate, and then the second step would be to detect topology from in the simplicial complex. So what do I mean by this? For example, can I see that my simplicial complex has holes without having a picture of it? Okay. So for example, how do I find holes? How do I detect holes? I can't find them because I'm really thinking of a simplicial complex as a combinatorial thing that's supposed to be modeling some topological space. And I want to detect in this simplicial complex the holes that are in the real topological space. Well, the kind of thing you can do is you're going to look for something like this in your simplicial complex. If you have edges from A to B, from B to C, from C to D, from D to E, from E to A, then you might have a chance of seeing a hole there. Okay? Now, there might or there might not be a hole. Well, let's just make it a little bit simpler. So, I mean, even like this, if you can find 3 vertices of your simplicial complex such that AB is an edge, BC is an edge, and CA is an edge, then you might have a hole. How do you check if that really is a hole? Well, you check whether ABC is in there. So if this is in, in the simplicial complex. Right, so if AB, BC, and CA are in the simplicial complex, where here I mean the set, the pair A comma B, etc. But if the triangle is not in the simplicial complex, then you have found a hole. Okay? And so this is the kind of thing that we're going to want to do. Okay. And so to do that, let me make some definitions. But if you guys have any questions, please let me know. I know that we just changed gears violently, and so I want to make sure that you guys are not really lost with what I'm saying. Question?
Yeah. So there's like another point behind ABC that, you know, next to like ABC, does that still count as a whole? Like ABC is still a whole? I guess I just want to know what a more precise definition of whole is.
So that's a really good point. So I was trying to make you guys fall for that, but you didn't. So this isn't necessarily a whole. Why not? Because it might look like a whole, but actually there might be some other stuff connecting. So it might be, it's a little bit more subtle than this, because it might be that this looks like a whole, but actually there's some other vertex here, D, such that ADC is a face, ABD is a face, and BCD is a face. And so maybe the ABC is not a face, but this doesn't deserve to be called a whole because it's just, this is just a cup, right? You pour water in there, it's not going to fall. It's going to land at D. And so this is the kind of thing that we're going to have to build into our construction of this homology group. Okay. I mean, in a sense, the answer that I might give you is a whole is an element of the homology group. I don't know. Do you like that answer? Well, I haven't told you what a homology group is, but I mean, of course, that's up to interpretation. What is a whole? I haven't told you. We need a theory of wholes. That's basically what we're doing. Okay, so I just need to make some definitions and let's do everything with this small example that we've talked about a lot. For example, this guy, we would like to say that it has a hole, right? This is an honest hole. And another characteristic that it has is that it's split into two pieces, and that's also a topological characteristic. You have two separate pieces, and these are the kinds of things we want to detect. Okay? So I'm going to take my simplicial complex delta. I'm going to take a field F. By the way, so if you've done this before, you might know that this guy doesn't have to be a field. It can be any abelian group. But life is going to be easier if I start with a field. So let me do it for fields, and if you want to be a little more ambitious, you can think about this being an abelian group. So I want to define a vector space. So the first thing I'm going to do is, for each I, I'm going to define Fi of delta to be the set of I faces. So faces of my simplicial complex such that they have I elements. No, so that the dimension is I. And remember that this means that this guy has I plus 1 elements. Okay? And then I'm going to make a vector space. And the way that you might think of this is it's a vector space such that this is a basis. Okay? I'm going to call this vector space Ci of delta. So I can just think of it as F to the Fi of delta. So you can think of this as column vectors, where for every element for every I face, you assign a number. Okay? So this is a vector space with basis call it E sub sigma over the sigmas in Fi of delta. Okay. So in this example, what do I have here? I have, for example, what's C0 of delta? Well, these are the zero faces. The faces of dimension 0 are the vertices. So I list the vertices like this. Okay? And so I can think of this as either a column vector that has an A entry, a B entry, etc. Or I can think of this as linear combinations of EA, EB, EC, ED, And I do it for all of them. So C1 of delta is going to be F of the edges, AB, AC, BC, BD, and CD. And so again, this is the vector space spanned by these guys. And so I can think of something in here as an element that looks like alpha times e to E sub AB plus beta times e to the AC, etc.